Gonna be terrible. Hello and welcome back to Calculus 1, section 2.3, techniques for computing the limits, or to compute the limits. So what do you do? Well, in the previous section, 2.2, we already said that you can graph and look at the graph. And number 2, we said chart. Now, in 2.3, we are going to introduce the method of plug-in, but you have to be careful. We'll talk about that. And then finally, algebra. So these are the methods that we use to compute limits. Now, as I mentioned before, the first two methods, what I call middle school methods, pick your x's, compute y's, and draw your conclusion from there. And we did that the last time. Here is an example from the last class where I had the function given up there, x squared minus 1. And what I said is you pick numbers that are leading to 3, and then you compute y's. And you look at the trend of those numbers. So we know that we want limit at 3. Here is the limit at 3. I pick the numbers leading up to 3, and when I compute y values in a function given, we see the trend over here is to go to 8. Oh, 7.4, 7.9, 7.99, it's getting closer to 8. From the other side, you have the same thing. All of these numbers are the numbers you pick that are leading towards 3, and then you compute their y values in the function. And you see that from 8.6 to 8.06 to 8.006, they're going to 8. So 8, 8, 8, the duck situation again, right? So that was the graph and chart method covered in 2.2. And those are the methods to solve limits that work 100% of the time, because you can always pick your x's and compute your y's. Right? It's annoying, it takes time, which is the reason why I call it the middle school approach. Right? It doesn't take a lot of cognitive power to do something like that. Pick x's, compute y's, and then look at the pattern. Now, we want to move on to the methods that we usually use. And the first one comes with a warning, and that's plug in. So, we talked about limit of x cubed minus 1 as x goes to 2. And we discovered that the answer was 8 by doing the chart. We also did the pre-calculus version of this problem where we computed at 2, and we got 8. So that means that in certain cases, in certain problems, we can just take this and plug in and get the answer. So why the warning? Well, it doesn't work all the time. plug-in method doesn't work all the time. Why and how? Well, in some cases, when denominator is 0, you might get the wrong conclusion, which means you just need to learn more as you progress through the class. So if you do the limit 1 over x and you say d and e as x goes to 0, yeah, if that was your guess, nice, you got it. So it worked this time and you're lucky. Here's another situation that you can have. Is the limit does not exist? No. I see some of you are shaking your head no. And that's true. The limit does not exist. If you take a look at f of x equal 1 over x squared, the graph for that function looks like this. So the limit is clearly positive infinity. As you approach from the left, as you approach from the right, they're both shooting up to positive infinity as they go towards 0. And now, another one of these sine x over x. Is this limit does not exist? Is this limit infinity? No. Does anyone know what this is? 1. Perfect. Ah! What I just did there is I divided 0 by 0 and I got 1. Power. Right? So, yeah, I'm sorry, but guessing is not gonna cut it anymore. Welcome to calculus. All right? We need to learn how to deal with these things. Right? 0 squared, which is 0, and there's 0. But look at the answers. Does not exist, infinity, and 1. So anything can happen. Anything can happen. So now the question is, how do we sort this out? Well, first off, these examples are important because these examples show to you that when you plug in a number and you get 0 in denominator, you immediately have to abandon that technique. You are not allowed to plug in numbers and try to compute limits if denominator is 0. Because you don't know what you're going to get on the other side. Any of those. Right? And the problem can be rigged, so this is any answer as well. 3/4 or 5. So the plug-in method works when the function in here is nice. If the function is nice, your answer is 7, everyone is happy, right? You're done. But as soon as you smell a 0 in denominator, the method of plug-in fails, and you have to resort to algebra or one of these guys. So let's talk about algebra. Algebra involves graphing as well. You know, all of the shifting of functions and reflection and all of the good stuff you learned in pre-calc. We need that for graphing approach. And algebra is the one that says, okay, we shift 2 units to the left, 2 units to the right. Right, those formulas exist. So that's all the part of graphical solution. And in algebra, it would be reflected as addition or subtraction to the expression. 1 over x versus 1 over x minus 2 versus 1 over x minus 2. Algebra is teaching you what this minus 2 does as it's put in a different position. So the first one is this. What is the second one? Let's go. I have no voice, you have to tell me. Come on, guys. All I heard is meow. It's all I heard from this area over here somewhere. Go ahead. Very good, thank you. Shift to the right 2 units. And how about the next one? So algebra will modify the graphs and you should be able to shift them. That's also the part of the geometric solution as well, right, when you graph the function. Now let's take a look at calculation. Limit as x goes to 5 of x squared minus 25 divided by x minus 5. The first impulse to solve a problem should be plug in. But if you run into a 0 in denominator, immediately abandon ship. Immediately. So we plug in 5, and I get 25 minus 25 over 5 minus 5. That's 0 divided by 0. Run. Right? Cannot plug in. Here, right in blood. Can you make the assumption that the answer does not exist? It's not no, it's hell no. There's a difference between those two answers. Okay. Alright? We cannot say it does not exist because we are going to see that the answer is 10. Right? So now we divide 0 by 0, we get 10. What? Oh, no, because it's, no, it's from home. Don't bash on my home. Now I'm angry, I have to quench the hellfires in me. Yeah, I don't actually know this. This is communicated through me. I'm a vessel. Anyway, what do we have? We have to use algebra to solve this. And does anyone know what is the thing that annoys us? It's this denominator of 0. And the question is, can we eliminate this denominator of 0?
X plus 5 times x minus 5.
Beautiful. We are going to factor and then cancel. So limit x goes to 5. And if you know your algebra, you see that the numerator cancels. I mean the factors, and then these cancels. We just divided 0 by 0 and got 10. Awesome. How does this look on a graph? It's canceling. X plus 5 is a linear function. Linear function that will go through 5. We have a linear function at 45 degrees, and this is very important. Open circle at 510. This point does not exist, but the limit does. It's 10. So, the function that you see is actually a linear function because the two linear terms canceled. And we have linear function as the answer, but we have to leave open circle at 5 because we cannot compute with 5. If you look at the original function, 5 is not in the domain. The canceled version of this function tells us that the function is just a linear line. So the canceled version gives us the final outcome of the graph, the line that you have to draw. And this over here gives you conditions on what numbers you have to exclude from the domain. In this case, 5. So this is a linear line with a single dot missing. Right? A single point missing. Now, if you have TI 83, 84, and you graph this function here with parentheses and everything you need, you are going to get a linear line. And if you zoom in on 510, you will see a missing pixel. That pixel will not be there, so the line would be interrupted. And you can try and do that when you have a chance. Just make sure you close parentheses after 25 before you divide to see that there will be a missing pixel which shows that you are not allowed to have 5 as the input because it has to be excluded from the domain because of x minus 5 in denominator, right? That gives us 0 in denominator. So we know now how to deal with this. Now, what did we learn in this example? Well, first of all, we learned that we reinforced the knowledge that we can't just plug in and hope to solve every problem. We also seen that 0 divided by 0 is 10 in this case, right? In the case with the sign up there was 1. So we can make it to be anything. That's the beauty of this. And finally, we've seen that one of the methods to solve the problems when you have 0 in denominator is to do basic factoring from algebra and then hope to cancel some of these expressions. Now, obviously, if nothing cancels, well, graphing the function and guessing the answer is the best you can do. But generally, right, we come up with the problems that you can cancel and, you know, show off your skills in that department. So most likely, if it's not canceling, factoring and canceling, you are doing something wrong. So one of the algebraic ways to do this is to do just basic factoring. Let's take a look at another example. Limit x goes to 16, square root of x minus 4, divided by no coughing, x minus 16. Do I want to switch this? Yeah, that's right. What now? I heard the word rationalize it. We can. What does it mean? Square root? How?
Multiplied by square root of x plus 4.
That guy over there. Nice. All right. And I will give you a tip. Do not FOIL the denominator. Just leave it as parenthesis times parenthesis. Let's see what you get. Times 7? No, that's no answer. Limit x goes to 16. When I FOIL, we get x minus 4 root x plus 4 root x minus 16 divided by x minus 16 times root x plus 4. These cancel because they're the same. And we get x minus 16 over x minus 16 times root x plus 4. Now these cancel as x goes to 16, and all I have is the limit x goes to 16 of 1 over root x plus 4, which is 1 over 8. Same problem. I want to do this problem differently now, and I call this the boss way. Hopefully we all agree that a squared minus b squared is equal to a minus b, a plus b. This is one of the basic formulas in algebra. Can I factor x minus 7? Can I factor x minus 7? Yes? Yes. I can write x as square root of x squared minus square root of 7 squared. So it's root x minus root 7 times root x plus root 7. You can factor whatever you want. It doesn't have to be perfect squares. As long as there is minus here, you can factor anything. So now I'm going to factor denominator and cancel it, and there is no need to rationalize, which is why it's called the boss way. Limit x goes to 16. The numerator is root x minus 4, and denominator is root x minus 4, root x plus 4. You can factor anything as long as you have minus sign. If there is a plus sign, your factors will be complex with i's, right? With imaginary number I. So the only thing that it's required of you to have is the minus sign here. In terms of factoring, you can have whatever you want over there. Doesn't matter what exponent is not, because you can always write it as the square root of whatever you have squared. And that immediately matches this. So you can factor anything. Okay. And now is the time for properties of limits. So these are the limit laws, properties of limits, whatever you want to call them. And they list 7. It's actually 6, but so here we go. Number 1 is the sum. Limit as x goes to a of f plus g is limit of f plus limit of g. All of these are f of x and g of x, obviously. They're functions. So I can split on addition and work on each term separately. Number 2, difference. Which is limit x goes to a of f minus g, and that's going to be limit f minus limit g. Three, constant multiple or scalar multiple. Constant. And multiply later by it. Product. Limit f times g is limit f times limit g. This rule works only for limits. It will not work later for derivatives and integrals. The first 3 rules also work for derivatives and integrals. Number 5, quotient. So quotient, you divide 2 functions, you can actually divide the limits. And I'll put 6 and 7 together. The power rule and the root rule. And it says if you have limit of the function f of x, which is raised to any m over n exponent. So guys, square is fine, cube is fine, but square root is also fine. You can take the limit of the function first and then raise everything to that m over n. If you are not remembering algebra, I'll remind you that x squared is x times x, that x cubed is x times x, that x to the 1/2 is the square root of x, and that x over, so well, let's go here, x to the n is x times x times x times dot 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 times x n times. So now if you have x to the 1 over, let's say, m, that's going to be the mth root of x. So this is where that last line 6 and 7, which I combine, it all depends what you have as your exponent. If you have a fraction in the exponent, then you have the order of the root and the order of the exponent. So if you have, let's say, x to the 7/4, this means 4th root of x to the 7. That's what it means. Now this rule here, this rule is allowing us to, instead of taking the limit of the whole thing over here, we take the limit of the function only, and then whatever value we get, we rise to the power that is there. So let limit of f of x be 3 as x goes to 5. Limit of g of x to be -5 as x goes to 5. Limit as x goes to 5 of age of x is, let's say, 13. So we don't know what these functions are. We just know what the value of the limit is. And now, this is what I call mathematical gymnastics. Limit x goes to 5 of f squared minus g divided by h. Well, if you pay attention during the limit laws, you immediately know what you can do. This limit can go in front of every function, keeping the form of the problem intact. So I have limit of f squared minus limit of g divided by the limit of h. And each one of these x goes to 5. Divided by 9. 14/9. And we're done. All I did is I swapped the entire blocks. It's 14/9, right? Oh, I plugged in the wrong number. Is it cool now? So this block is this block. So you swap it with what is equal to, and it's 3. And then this block is this block, and you get your -5. So you can come up with whatever you want, and you can make these problems on your own and just chase stuff around. So those are the limit laws. And the last concept in the lecture is the Squeeze Theorem. also known as the sandwich theorem, depending on which book you read. I like the name, sandwich, because that's exactly what you are doing. This is designed for an erratically behaving functions like sines and cosines. See, the problem with sines and cosines is they are periodic, and unless you freeze them in space and time, you can't find the limit. And you say, what's the limit of sine as x goes to infinity? Well, it's continuous wave. There's no limit. It's bounded between -1 and 1, but there's no limit. Because in infinity, it takes on all of the positions at once. So if you have a trig function floating around, the best bet is to use the sandwich theorem or the squeeze theorem. So now, what is this theorem about? Well, it's exactly what it says. So what do I have over here? A piece of bread, a slice of cheese. If you like to simplify, put 2 slices. And then a piece of bread on top as well. Right? Sandwich. This is the bad function. Right? Sandwiched in between 2 functions that are easy. The idea is, no matter where I take these 2 functions that are squeezing the one in between has to go to the same place. So as I move the sandwich around, right, I'm not touching the cheese, right, I'm holding over the bread. As I move this around, the cheese goes wherever the bread goes. So, if I am able to squeeze the badly behaving function in between nice, easy behaved functions, then the limit is forced to be the same. Because, look, as I said, the thing that it's sandwiched in, I'm not touching it, and it's going everywhere, wherever I take the easy to grip, let's say, parts. No mess, or whatever. So now, if I have the famous example is limit x goes to 0 of x squared sine 1 over x. This is the famous example. What you have is a sine function which says that's what you have. So now you're looking here and you're going, is it 0? Is it 1? What's going on? The oscillations for the sine function are so fast that we cannot measure. The oscillations are going to infinity. The speed of the wave at that point is infinite. And we cannot determine what's the limit. So what do? Well, we try to sandwich this in between two functions. The one on the bottom and the one on the top. And if they all meet at the same point here, because we are looking for the limit at 0, if the both blue and red give me the same value, the function that it's squeezed in between has to give you the same value, because cheese, right? So what do? I build these functions. I know that sine function is bounded by 1. Sine function can never return a value bigger than 1 or smaller than -1. So the entire sine function, or cosine for that matter, is a wave that it's always trapped in between -1 and +1. So now we can write that as sine 1 over x in between -1 and +1. Great. Compare this to this. Are they the same? Okay, what's different? X squared. So let's make it the same by multiplying all three sides by x squared. What we get is -x squared less than equal than x squared sine x 1 over x less than equal than x squared. There's your -x squared, there's your sine function, and there's your +x squared. Are these end functions easy to deal with the limit? They are, right? So this side over here is your blue side, and the limit as x goes to 0 of -x squared is 0. This over here is your red side. Limit of x squared as x goes to 0 is 0. Well, what do you get to squeeze in between 0 and 0? No, another 0, exactly. So both of these imply that the limit of x squared sine 1 over x is 0. Does this make any sense?
Yeah.
Yes? So what's the problem here? Problem is you must come up with those functions. You don't get to put anything, right? That function that you have in the statement of the problem, which should contain calculus. Sines and cosines. Sines and cosines are bounded by 1. This is the $1 million trick. All right? Are we going to use this method to compute the limit of x cubed? No, it's basic function. You just use the previous methods. This method is designed for these bad situations where you have trig which oscillates and you have no clue what the value is. Bye.